Okay, this is chapter 2, part 5, and we're going to pick up with the uniform circular motion. So if we have an object that's in uniform circular motion, it's going to have a constant speed, but it's constantly changing directions. So the velocity is therefore going to be constantly changing. And because there's a change in direction, that means there's going to be a change in acceleration. The direction of the acceleration is at a right angle to the velocity, and it points toward the center of the circle. So you can see in this picture, centripetal means center-seeking acceleration, and it's supplied by the friction of the tires of a car as that car is going around a track. So the car is going to remain in that circular path as long as it's going to have enough centripetal acceleration to keep it there. Okay, and you can notice how all the vectors for centripetal acceleration are pointing toward the center of the track. Now, if we want to calculate centripetal acceleration, we use a sub C by the A to let us know its centripetal acceleration, and that is a V squared over R. So that would hold for an object that's moving at a constant speed in a circle with a radius of R. So when we look at this equation, we can see that centripetal acceleration is going to increase with the square of the speed. And we also see that as the radius decreases, it's increasing. So centripetal acceleration and speed squared are directly proportional, which means you increase one, you increase the other, whereas centripetal acceleration and radius are inversely proportional, which means when one increases, the other one would decrease. So let's look at our first example that they give us in the PowerPoint. So you're asked to find the magnitude of the centripetal acceleration. So we know that we're looking for A sub C of a car going 12 meters per second. So we know that is our speed with a radius of 50 meters. Okay, and we know our formula for centripetal acceleration is AC equals V squared over R. So we've written down everything we're given, and then we put it into our formula. 12 meters per second squared, so not only are the units squared, but also the magnitude is squared, divided by 50, which will give us 2.9 meters per second. And that should be meters per second squared, because you're looking for centripetal acceleration. And remember, acceleration always has a square for the seconds. So here's another one. You're asked to compute the centripetal acceleration in meters per second squared. So you're looking for AC of the Earth in its nearly circular orbit around the Sun. So you go to a table and you find the radius and also the speed. Okay, so all we have to do is take our speed, which is 3 times 10 to the 4th meters per second, and that whole quantity is squared, divided by R, 1.5 times 10 to the 11 meters, and we get our answer to be 6 times 10 to the 3rd meters per second squared. If you do not get this answer when you punch it into your calculator, you could be inputting the scientific notation incorrectly. Remember, you never hit this. X doesn't refer to a times key. So you would put this number in 1.5, and then you would do your EE or your EXP, and then press 11. So you don't want to hit that multiply key. Okay, let's have a couple other problems that we can try. So in this first one, we have a rock that's tied to a string that's moving at a constant speed of 8 meters per second. So our speed is 8 meters per second, and it's moving in a radius of 7 meters. You're asked to calculate the approximate magnitude of the centripetal acceleration. So you're looking for AC. Okay, so we know that AC equals V squared over R. So we have 8 meters per second. And all that is going to be squared divided by R, which is 7 meters. And that's going to give us an answer of 9.14 meters per second squared. We wanted to adhere to our significant figures. This has 2 significant figures because it has that decimal place. So if we wanted to put our answer into significant figures, we would just say 9.1 meters per second squared. Okay, and then let's try this one. We want to look at the magnitude of the acceleration of a car going 12 meters per second. So we know the speed is 12 meters per second on a circular clover leaf with a radius of 50 meters. And you're looking for centripetal acceleration. So once again, AC equals V squared over R, which is going to be 12 meters per second. That's all squared divided by R is 50 meters, and that's going to give you 2.9 meters per second squared. Okay. So what I'll talk about is projectile motion. So projectile motion, when you look at it, you have an object, you throw it horizontally. It's going to combine straight line as well as vertical motion, and they're both going to be independent. So if I neglect air resistance, that horizontally projected object is going to be traveling in that horizontal direction with a constant velocity. So horizontal direction with a constant velocity. It falls due to gravity. So horizontal constant velocity, which means if it's a constant velocity, it has no acceleration in that horizontal direction. So in this figure, we see that it's a multi-flash photography of the 2 balls. So the yellow one was projected horizontally at the same time as the red one was dropped vertically. And what you see is that both balls fall vertically at the same rate. So they wind up at the bottom, even though one was projected horizontally and one was just dropped vertically. And in this picture, what you see is your velocity in your horizontal direction doesn't affect the velocity and acceleration in the vertical direction. They're independent of one another. So what we're looking at here is this curved path that you see in the picture on the right. It's a result of the combined motions in the vertical and the horizontal direction. So if you notice, as the ball goes up and down, it's traveling to the right. And what you get is a combined effect of that curved path that you see. So you throw a football. Well, if we neglect air resistance, that football is going to have the same horizontal velocity throughout its flight, but your vertical velocity is going to change. Okay, just like you would be throwing it upward. So if you notice, horizontal stays the same, is constant. It's the vertical velocity that's changing. Okay, all these arrows in the horizontal direction have the same length. The arrows in the vertical direction do not. They're changing. And then we also see that if we don't consider air resistance, what we notice is the projectiles are going to have symmetrical paths. Maximum range is going to be 45 degrees. Now this is in the absence of air resistance. Okay. But we know we don't live without air resistance. We have air resistance. So what you see in this figure is the plot where you have air resistance, and notice they're not symmetric. Okay, it's going to reduce the horizontal velocity. So I've given you a list of just things that athletes have to consider with projectiles. So I'm just going to mention a couple. You know, what angle are they going to release the football? Let's say football. Are they going to put a spin on the ball? What kind of spin? If they're playing outside, what kind of wind is going on? What's the direction of the wind? And so forth. So all of these points have to be taken into consideration. And then the last slide in Chapter 2 is just a summary of formulas. You have these formulas on your formula sheet, and remember, for the exam, you may use the formula sheet as well as the conversion sheet. Okay, this ends Chapter 2's lecture notes.